Balancing performance and water hygiene. DHW systems present perhaps the greatest challenge in building water engineering. Unlike space heating systems, where the primary objective is the efficient transfer of heat, DHW systems must satisfy several competing requirements simultaneously. They must provide adequate hot water at the point of use, minimize energy consumption and standing losses, and maintain conditions that discourage microbiological growth throughout the distribution network. The principal microbiological concern is the control of Legionella bacteria, which can proliferate where water remains within favourable temperature ranges for prolonged periods. HSG 274, published in support of the Health and Safety Executive's HSE's Approved Code of Practice L8, recommends that hot water is normally stored at not less than 60 degrees C, while secondary circulation systems should return water at temperatures of at least 50 degrees C. Achieving these temperatures consistently depends as much on the hydraulic design as on the heat source itself. In smaller domestic and light commercial buildings, this is often achieved simply by minimizing distribution volumes and keeping pipe runs shorter. Larger buildings, however, generally require secondary circulation systems to maintain hot water temperatures, reduce waiting times, and minimize water wastage at outlets. A calorifier, the insulated hot water storage vessel, may generate water at the correct temperature, but unless circulation is properly balanced, some parts of the network will inevitably cool before water reaches the point of use. Poorly balanced return circuits often result in some branches receiving excessive circulation, while others remain below the intended operating temperature. For this reason, the design of secondary circulation pipework deserves the same attention as the supply distribution. Return circuits should be sized to accommodate the required circulation flow while limiting pressure losses and heat layout loss. And layouts should minimize unnecessary deadlegs and ensure that all branches receive adequate circulation. Hydraulic simplicity is generally an advantage. Good design alone, however, is not sufficient. Before any system is brought into service, it should be thoroughly cleaned and flushed to remove construction debris and installation residues. Guidance on pre-commission cleaning procedures is provided in BISRIO BG29, reflecting the importance of commissioning in achieving long-term system performance. Systems that are straightforward to understand are usually easier to commission, maintain, and adapt as building use changes over time. Commissioning is the stage at which design assumptions are translated into operational performance. Even the most carefully designed system cannot perform as intended if balancing valves are incorrectly adjusted, circulation rates are inadequate, or flushing procedures are incomplete. Successful commissioning therefore verifies that design temperatures, flow rates, and pressures are achieved throughout the network, while also confirming that cleaning, flushing, and disinfection have been completed in accordance with BS 8558, BSEN 806, and HSG 274 as appropriate. Automatic balancing valves, temperature monitoring, and intelligent flushing systems are becoming increasingly common in larger water systems. By responding to changing operating conditions, they can help maintain hydraulic balance and water quality, while providing building operators with better information on system performance. Such technologies complement good hydraulic design and commissioning, but cannot compensate for poor design or installation. Cold water systems deserve equal attention. HSG 274 recommends that cold water should normally be maintained at below 20 degrees C, yet achieving this target is becoming increasingly difficult as buildings become better insulated, summer temperatures increase, and water consumption falls. Water-efficient fittings, intermittent occupancy, and pipework routed through warm ceiling voids or service risers can all increase water age and allow temperatures to rise above the recommended levels. Good design remains the first line of defence. Cold water pipework should be routed away from heat sources wherever practical, insulated appropriately and designed to minimise unnecessary stored volumes. Short branch connections, sensible pipe sizing and layouts that encourage regular water movement all contribute to maintaining satisfactory water quality. Where periods of low demand are unavoidable, operational measures may be required. Routine flushing has traditionally been used to replace stagnant water, but manual flushing is labour intensive and can consume significant quantities of potable water. Automatic flushing systems offer a more targeted approach, initiating flushing only when predetermined time, temperature or usage criteria are reached. In addition to helping maintaining water quality, these systems can provide valuable operational data, enabling facilities managers to identify areas of the network that experience little use and may require further investigation. Whether the system serves heating, hot water or cold water distribution, the underlying engineering principles remain consistent. Good performance depends upon understanding how layout, hydraulic balance, material selection and operational management interact. Intelligent technologies can support these objectives, but they cannot compensate for poor design. Reliable water systems are created by integrating sound engineering principles from the earliest stages of the project through commissioning and into long-term operation.